Hi friends, welcome to the series on lectures on electromagnetic fields. In previous lecture, we have seen the definition of inductance. Now in this lecture, we try to understand how to evaluate inductance of a solenoid. So a solenoid is nothing but a conductor that was wound in the form of a circular circle. That means a solenoid will have a circular cross section. Here, you suppose that we took a conductor of length a particular length, say let it be some 44 meters. Then this 44 meters conductor can be bent in the form of a circle having a radius of 7 meters. You know that the length is the circumference of a circle is nothing but its peripheral length. So the peripheral length or the circumference of a circle is equal to 2 pi r, which is equal to its peripheral length. So the peripheral length should be equal to length of the conductor. Then the radius r is equal to 44 divided by 2 into 22 into 7, which is equal to 7. So as I told you in the last class, this one circular path will be treated as a single turn. This will be treated as a single turn. So if you reduce the radius, then what happens? The number of turns increases. Obviously, as you reduce the radius of the conductor, then what happens? The perimeter or the circumference of the circle decreases, so that you can get more number of circles, so that solenoid will be a coil that is having a circular cross section like this. So here this is turn number 1, turn number 2, turn number 3, so on. Will be having n number of turns. If you arrange all these turns on one over other, then we will get some length. Let L be the length of the solenoid. Then it is not the length of the conductor, it is the length of the solenoid. Please understand. Then or maybe the radius of the circular coil. So here each circular coil will be having equal radius. So this R we call it as radius of solenoid. Solenoid radius or solenoid coil with radius we use. Let I be the current that was sent through the solenoid. Because of that, there establishes a magnetic flux in it, so that the direction of magnetic field would be like this. So I is the direction of current. Okay. So what we need to find out? We need to find out the inductance of this solenoid. As per the definition of inductance, L is equal to N pi by I. We know the definition of inductance. It is the ratio of flux linkages to the current which they link. So the flux linkages is equal to N into pi, because the solenoid coil is containing N number of turns and pi is the flux produced in it. This pi is produced because of this current I. So this n pi are linking this current I. So that the ratio is n pi by I, which is equal to L. So that we need to find out the value of pi. So if you can find out the value of pi, then our job is very easy. We can find out the inductance of a solenoid. So to find out the value of pi, first we need to evaluate magnetic flux density. Magnetic flux density is V is equal to mu naught H. We know that magnetic flux density and the magnetic field intensity are related as B into mu naught. B is equal to mu naught H, where mu naught is the permeability of the medium. So for a solenoid, the value of H is equal to N by I, N into I by L into Az, where Az is the direction of magnetic field intensity. So that here mu naught into N by L into I Az. Now here we take N by L as N is nothing but number of turns per unit length. Number of turns per unit length. So that B is equal to mu naught small n into I Az. Now let pi be the flux that was established in each coil or each turn. Then this pi and B are related as integral over the closed integral over the surface B dot ds. So we know the value of B, and the surface area of the solenoid or the circular path is equal to, the differential area is equal to rho d rho d pi d Az. The differential area of the surface is equal to rho d pi A z. So if you substitute these values in the above equation, we can write it as, or first we evaluate what is the value of B dot ds. That is equal to, B is equal to mu naught N I A z dot rho d pi Az. A z. So which is equal to, because it is the dot product, Az dot Az is equal to 1 mu naught N I rho d pi. So this is what the value of pi that links with each turn of the coil. Each turn of the coil. Now, or but this is the differential, sorry, it is not the flux, it is the differential flux that links with each turn of the coil. Now, to find out the flux, pi is equal to integral over the closed surface d pi, which is equal to r varies from 0 to r, where r is the radius of the coil, rho value varies from 0 to r, and d pi and pi varies from 0 to 2 pi, and we substitute the value of d pi here, mu naught ni rho d rho d pi. So after integrating and substituting the values of all the parameters, we are going to get this value as mu naught n into I is constant. So I brought out these values from the integral. Rho value varies from 0 to r, rho d rho, pi value varies from 0 to 2 pi d pi. So which is equal to mu naught ni rho square by 2 0 to rho and pi 0 to 2 pi. So 2 pi into mu naught ni r square by 2. So 2 will get cancelled, which we can write it as mu naught into pi n I is the total flux that links with the flux that links with each coil. There, L is equal to n into pi divided by I. So n by I into the value of pi is mu naught pi small n into I. I will get cancelled, which is in turn equal to mu naught pi small n into capital N. So where capital N is the number of turns. So by taking the, sorry, here I forgot about to write r square is r square. Here the small capital N is nothing but number of turns. The relation between small n and capital N is small n is equal to capital N by L. So we replace n with small n into L, where small n is the number of turns per unit length and L is the length of the solenoid. By doing so, what we are going to get is mu naught pi n small n into L r square, which is equal to mu naught pi n square r square into L. Henries. You know that Henries are the unit for inductance. This is the inductance of the solenoid having a length of L meters. So from this we can find out inductance per unit length. Inductance per unit length. Is equal to total inductance divided by the length of the solenoid coil, which in turn equal to mu naught pi n square r square L divided by L. This 2 we get cancelled, which is equal to mu naught pi square n square r square is the inductance of the solenoid coil per unit length. So, in this lecture, we find out the magnetic flux or the flux linkages that are linking the solenoid coil, and inductance of the solenoid coil and inductance of the solenoid coil per unit length. I hope you understood the lecture. For better understanding, I request you to watch the video thoroughly and stay tuned to my channel for some more videos on electromagnetic fields. Thank you for watching my channel. Bye.